13A. Here we go, some year 11 terminologies. What is a set? Again, someone tell me, what is a set? Let's go with Chi. What is a set? Group of numbers, could be a group of letters, a group of anything. Okay? A group of anything is called a set. How do you denote a set though? How do you denote a set? No, that's how you list a set. How do you denote a set? How do I know I have a set? How do you show that I have a set? A what? No, that's to list a set. E is an element of? You're talking about this E? No? Not that one? That's an epsilon. Epsilon symbol for universal set. I actually wrote it there. Usually denoted with a capital letter. Okay, so yes, you're right, it has curly brackets, but if I want to talk about a set A would be something like this. Capital A equals 2, and then you say curly brackets, A, B, C, D. That's called a set. So in this particular set, I have A, B, C, D. Okay? If I want to do another set, I can do capital C. It has letters G, H, I. Okay? Then now I can say something about these A and C's. I could say A and C, A either intersects with C, but it doesn't. Nothing intersects with C, so is what we call a null set. Okay? But that's how you denote a set. A capital letter represents a set. We use braces, these curly brackets, to list. Anytime you need a list, you use curly brackets. If it's not to list, if you're talking about an interval, that's when you use open and close brackets. Okay? Commas in between to list the elements. Things inside these braces are called elements. Okay? I've just used an intersection there, which means common. Here we go. Oh, I already gave an example there. Oh, I was ahead of time. And I just told you what an element is too. Okay? Elements are things inside a set or a given point. So, let's go to the next one. What is a universal set? So now you know what a set is. What is a universal set? What's a universal set? Jerry? Not sure. Daniel? Yeah, everything that you could have. So when I talk about a universal set of rolling a dice, it would be 1 to 6. But a set A could be any group of numbers I want. I could say group A has only the odd numbers. Okay, but a universal set tells me the universe of that particular group. Okay, and that symbol that you generally use is that little squiggly E that I did. Okay, so how I do it is I draw a loop, and it comes in and it comes back out. Okay, it's called your epsilon symbol. You don't have to do it like that. Normally you can just do little E like that, and that's fine. Okay, but that E there represents your universal set, and that's when you say, so rolling a dice, for example, would have 1, 2, 3, 4, 5, 6. So using that symbol now indicates I only have 1 to 6. I have nothing else. Then within that group, I can say A, set A represents the even numbers, so 2, 4, 6. Set B could be 2, 3, and 5. Okay? That's like an example of a set. So these are groups within the universal set. Okay, so you can think of it as this is the superset, these are the subsets. If I drew a diagram of it, you can think of it as this is the universal set, and you got A, and you got B. Okay, that's what it looks like. Cool. All right, so we've got a universal set. What else did you learn? Rolling a dice, 1, 2, 3, 4, 5, 6. That's the E symbol, by the way. Or epsilon symbol, and that's the picture.
If your universal set is, say, all real numbers,
yeah,
and then in like the outside area, you can say like soft bracket biggest number that's included, comma infinity bracket, and the same thing for negative.
Yep.
Right.
What is a complementary set? What's a complementary set again? What is that, Zahn? So your set we know is a group of things. Complement is usually used with a dash. So if this is A over here, actually, if A is 1, 2, what does A dash mean again? That's A complement, not 1, 2. So out of my universal set, I had 1, 2, 3, 4, 5, 6. If A is 1, 2, then A complement has to be not 1, 2, so 3, 4, 5, 6. Okay? So complementary set is what it isn't. So it's the opposite of that, or the not having that. Okay, so the example there, like I said, for example, above, A complement would be 3, 4, 5, 6, since A is already 1, 2. So if you draw the diagram, which I think I've drawn wrong, actually. Yeah, this should be A, and that should be B there. See, A represents this, which I've sort of tried to stroke through that. There we go. That's A, and everything that's not in the circle, the green circle, is a complement, which you can see the numbers are 3, 4, 5, and there's meant to be a 6 somewhere as well. So there. Okay? There you go. Let's do the next one. So these are just some common terminologies you learnt in Year 11, the very basics of Year 11, which also links to Year 10. Okay? Let's go back down to now. Universal set, 1, 2, 3, 4, 5, 6. A is 2, 4, 6. B is 3, 4, 5, 6. Here's my pictures here. Now, when I use this symbol here, what does this symbol mean again? Union. What does union mean?
All elements of both sides.
All elements of both sides. Now, you notice that B has 3, 4, 5, 6. A has 2, 4, 6. Why is it that I only have 1, 4? Good. Elements only occur once, okay? It doesn't repeat. So that lends itself to the formula now. Anyone remember the formula for A union B in terms of elements? What was it equal to again? Good. Because that's what they both have in common. So in this case here, they both have in common a 4, but you can't write 4 and a 4 again. So if you write all the list of A, which you have 2, 4, 6, if you group it with B, which again is 3, 4, 5, 6, actually there's 2 commons there. All right. And then minus what's intersection or what's common between the 2, you got 4 and a 6. That's how you remove the commonalities and you end up with 2, 3, 4, 5, 6. Okay? So that's called the addition rule. That's one of the first things you learned back in Year 11, and it's something you're going to revise again. And this is a common rule when you're doing your Saxo exams. I promise you that it's going to come up one somewhere where you're going to be using that rule. That's called the addition rule. Okay? Normally it looks like this. Normally addition rule comes with probability. So they'll say probability A union B equals to probability of A plus probability of B minus probability of A intersection B. Okay, that's called the addition rule. This means intersection. What does intersection mean again? What do they have in common? Okay, so intersection is what they have in common. Now, when you're looking for the probability, now I'm just going to backtrack a bit. Let's say when I roll a dice, actually I shouldn't say roll a dice. Let's say I pick T-shirts in the morning and pants. And then after that, I would choose socks. And I've got 3 socks. Okay, socks. I got a black sock, blue sock, yellow sock. Okay, and the same thing. Black, blue, yellow. Well, I told you in terms of the chances of me choosing a shirt, I'm like, well, you got half a chance. Actually, no, I'll do a third of a chance. Okay? And then pants, I got now 2/3 of a chance to choose pants. I have one or the other. Okay? And then let's say choosing black socks, I've got, I don't know, 1/6. This is 3/6. So 1/6, 3/6, and what's that? 2/6. Okay, those are my chances of getting blues. If I ask you to find the chances, so probability of getting a T-shirt and, which I'm using intersection, and I want a yellow sock. How do you work that out again? So I want to know the chances of me picking a t-shirt and a yellow sock. I want to get a t-shirt and a yellow sock. What do I do? So which two probabilities do I multiply? Good. This is called the multiplication rule, okay, which later on will link to conditional probability. But when you're when you're saying and or intersection, you're actually doing this branch by this branch. We're multiplying that, okay, because we don't know how many groups we have for t-shirts, and then for every group of t-shirts, I've got X amount of groups for the other second option. So that's why we times them, okay? So in this case, yes, you're right. It would be multiplying 1/3 to 3/6, which gives me 1/6 of a chance to choose a t-shirt and yellow. What's the difference between this and if I had asked you to find the probability of getting yellow socks? So how do I find just yellow socks now? So you can find and, t-shirt and yellow. We know the chance of getting t-shirt is 1/3. We know the chance of getting pants is 2/3. But what if I asked you, what's the chance of getting yellow? Providing that this is all the same. So that's 1/6, 2/6, and 3/6. How do I find yellow? Chance of getting yellow. Good. You want to know all the chances. What's the total probability of getting yellow? To get yellow, I could either get a t-shirt and a yellow, or I could get pants and a yellow. That's the total probability of me getting yellow. Yeah? So what you have to do is you would have done 1/3 times 3/6 to get one possible yellow, so TY, and then you can have PY. Okay, you have to add those two. Now because they're separate branches, that's why you add them. But when you multiply, when you're going across the branches, that's when you multiply them. Okay, so when you're going across branches, you multiply, but in separate paths, you add them together. So in this case, if I want to find the chance of yellow, I have to find, so probability of getting yellow is equal to probability of T intersection Y plus probability of getting pants intersection Y. Does that make sense? So if I color code it in terms of highlighting in green, I have to work this one out as well. Add those two together. Okay? All right, that's just a quick revision of, in terms of probability, how you find the probability and using tree diagrams there. Okay? Now, let's push this to the third part. What's mutually exclusive mean again? Luke. It is?
They don't interfere with each other.
What does that mean?
So on your Venn diagram, your A set and your B set have no intersection.
Very good. It has no intersection. That's the key word for mutually exclusive. It's just when probability of A intersection B is equal to 0, because we're talking about probability. Means chances, it's 0. So it's when A and B are separate. Now this gets confused from last year with the word independent. What's the difference between independent events and mutually exclusive? Because a lot of students get those two confused. What's the difference between mutually exclusive and independent events? Yes. So how do you prove that? So if you were in a tested exam and they said, show that these two are independent events, what do you have to do to show it?
It's a like probability of A intersection B is probability of A.
Good. Excellent.
Or probability of B.
Yeah, perfect. That's exactly it. So I'll just take a step back. The difference between mutually exclusive and independent events, mutually exclusive is pretty straightforward. It's just when the intersection is nothing. There's no intersections at all. Okay, this is mutually MUX. Okay, mutually exclusive. Independent events, when you're drawing your tree diagram, okay, you would say something like this, and I'll relate it so you can see the difference between the two. Let's say if Monday rains, I'm going to do M for Monday rains. M dash means Monday doesn't rain. Now, if I told you there's a 30% chance that Monday rains, then that means there's 70% chance Monday doesn't rain. True? Now, on a logical basis, if today rained, would it affect tomorrow raining or doesn't it affect it? Logically, if today rained, what's the chance? It does depend. Yes, it does depend. Now, is it more likely or less likely to rain?
It depends how intense that rain was.
Okay, but what you just said is it depends. Yeah? Whatever happens is it doesn't stay the same. So if it's 30%, you can't say, yeah, tomorrow's got to be 30% as well. That's what you wouldn't say. You wouldn't say that tomorrow's 30% and the day after is still going to be 30% and the day after that is still going to be 30. That's what you wouldn't say. But you would say it depends whether it's winter, whether it rained a lot today and what time it rained. Yeah. Maybe it rained at 12 a.m. at night, then yes, maybe it's likely to rain. Yeah? So your point is that the chances for Tuesday raining will now likely depend on a lot of cases about Monday. So when did Monday rain? Whatever it is, yeah? This is called dependent events. When the next day is dependent on the previous day. Why doesn't it rub off? Ugh. Okay, you know what? Screw it. You have two possibilities here. M, not M. This is Tuesday, Tuesday not, Tuesday, Tuesday not, right? Yeah. What I want to illustrate here, the difference between these two, which I'll do it again, M dash, Tuesday, Tuesday dash, Tuesday, Tuesday dash. What makes independent events different from mutually exclusive is right here. If it's independent, it means that if Monday rains, tomorrow's going to be exactly the same chance. It doesn't matter what time it rains. It doesn't matter which day, which season it is in. It is always going to be 30%. That's what independent means. Independent means that I don't care if I looked at a month from now or a year from now, the chance of raining is still 30%. It will never change. And an example of that is flipping a coin. See, it doesn't matter how many times you flip the coin, it's still a 50-50. It's always going to be a 50% chance. If you flipped it 100 times or you flipped it for the third time, it doesn't affect what you got in the previous one. That's called independent events. Whereas dependent events would be, in this case here, if this is 0.3, it's likely that this will change. And then it would likely mean that Wednesday will also change as well. It's all dependent. So how does that change in terms of your mathematics and how do you prove it? 0.3 times 0.3 will tell you the chances of Monday raining, so Monday and Tuesday raining. But because if they're independents, it's going to be the same as Monday. If they're independent, it means the chances of Monday and Tuesday raining, well, it's exactly the same as Monday because it's still 30%. Okay? That is called, what I've just described there is called independent events. Okay? When probability of one is exactly the same as the other. Okay? Or technically, another way of thinking about this, which I'll fix it, probability of m times probability of t, yeah? So I'll write it again. Probability of m times intersection t is equal to probability of m times probability of getting Tuesday. Now it's getting a bit messy, so I'm going to do it again. Whereas, why is that true? So probability of m intersection t is equal to probability of m times probability of t. That was proven through the tree diagram, right? So m, t. This is independent. Now, when it's not dependent, then this is what it'll look like. Probability of m intersection t is equal to the chances of Monday raining by, okay, now I'm going to highlight, it's exactly the same branch. It's still this times this. But you do not say the chances of t, chances of getting t, is not the same as chances of getting t anymore. This is now chances of getting t depending on m. Now, I don't know if you remember this part here. Oh, yeah. This is conditional probability. Because this is called independence because we're saying chances of t is still going to be t. It doesn't depend on m. So that's why it's 30%, 30%, 30%, 30%. When it comes to dependent events, we're saying that this is still itself. But the next one, to get t, it depends on m. That's why we say Tuesday given, which means depending on whatever m is. It's dependent on. This right here leads to last year's concept, which was the hardest one in year 11 for students to get, was that if you rearrange this is PR m intersection t, you divide both sides by probability of m, you get probability of t given m. This was last year's formula for conditional probability. And it's only coming from independent events. So this is the theory. The theory says that there's two types. There are two types. One where the second event doesn't depend on the first one, or one does depend on the first one. Okay. And that's where you learn conditional probability. That was the rule for conditional probability, and they gave this a name. They called that the multiplication rule. Okay, but it's not a multiplication rule or anything. You're just following the tree branch. You're still multiplying this by this, but it's just, what is that representing? Is this dependent on m, or is it just by itself? So if you're in an exam and they ask you to show or prove that it's an independent event, that's all you got to show. You're just going to show that the chances of getting n times chances of t is exactly the same as chances of m intersection t. If you can prove that, you're done. Okay? Or if you prove it otherwise, then you prove it's not. That's all you have to show. So that's the one formula. It's only one short question or exercise that you have to do when the question asks for that. But that's the difference between independence and this is conditional, hence leads to multiplication rule. So multiplication rule becomes conditional. Okay. Yes, Daniel.
So if I got a conditional probability question,
Yep.
can I just answer the method like the tree diagram or like the formula?
You would do both. Most likely, if they give you a conditional problem, they would want an answer. And so you can use, I use tree diagrams to explain it to you guys and do it myself as well. And then I answer it by multiplying them. But you don't have to write this out. It's normally because students will confuse between the two, the first one and the second one. When they draw out the tree diagram, it only makes a difference on that branch. So if you have an independent problem, these will always be the same. If you have a dependent problem, these will just start changing. And that's the only difference in terms of calculations. That's where it will be different. Okay? But there you go. Now, that's talking about independent, dependent, mutually exclusive. Last one for 13A that you need to know. Once you know your tree diagrams, this is just your probability properties. Karnaugh maps. For those who've forgotten, this helps you to do conditional probability easier. Okay, but it's just a tool. It's like a tree diagram, it's like a Venn diagram, then Karnaugh maps is exactly the same. How this works, this is your Venn diagram. So once you learn how to use your Venn diagram, you got to learn the symbols here. Everyone knows this one. A intersection B is what they both have in common. Everyone knows that one. It's the next three, or next two that most students don't realize. A intersection B dash means I have A, but I don't have B. See, this is B. If you were to color everything that's not B, it will be this entire thing. Yes? But out of this entire thing, which one has A as well? So out of this entire thing, only this section has A. That's why that's called A intersection, which is in common with not B. So this is not B, all of this is not B, but where is all that? Also overlapping with A, which is only this red section here. Okay, this one makes sense. A intersection B, so this is all of A, this is all of B. Where do they overlap? Clearly there. Yeah. This one is saying everything that's not A, so everything that's not A is all around the red. But where is that overlapping with B? Only in this section. Okay, there's your two, and then finally everything that's not A, which is all the way outside. Everything that's not B, everything all the outside. Okay, where are they both overlapping? And you can see that because it's not A, there's only the outside of the shapes. Not A, not B. That's how you get the outside. Okay? Now that's represented in what we call a Karnaugh map, which is here. And this is saying you've got A dash, B, B dash. Now this is going to be very useful when we get to conditional probability. Okay? But this is just saying we're representing intersections. So this is where A intersection B is. This is where A intersection B dash is. If you actually really look at it, A intersection B, which I'll color in here, A intersection B dash is here. What I've just colored is all of A, which is why when they say if you add across, it should give you the total of A. This should give you the total of A dash. If you add down, this should give you the total of B, and this should give you the total of B dash. And that's going to be useful because when you're talking about probability, we all know that chances add up to 100%. Okay? And that's where it's useful when you're working with probabilities. In your exam, I promise you, I can find some. Actually, I got some here, actually, for you to look at. And it's so easy to do, but kids will forget about these ones. Here, I'll show you. Let's look at an exam question. 2011, not too far ago. Let's have a look at this one. You technically have all the skills, and what I just revised is a 13A problem. You should have all the skills to get 3 marks. Question 8 of exam 1. Pretty simple. 3 marks. 3 out of 40. Let's have a look. It says 2 events A and B are such that they tell you what probability of A is. They tell you what probability of B is. They say if A dash denotes the complement, so now you know what the complement of A is, calculate that. See what I mean? Students normally don't like complement with B. If it was A intersection B, you guys have no issues. But when it says probability of A dash intersection B, students may find it tricky. Now, it says, I want you to find this when A union B equals 3/4. How are you going to begin the first one? So this is what you know. All you know is A union B, chances of that is 3/4. You know probability of A, 3/5. You know that probability of B, 1/4. What have we learned so far? What can we do to solve this issue? We're trying to find probability of A, A dash intersection B. What rule should I use? Maybe that's the first step. What rule should I use? Addition rule. Why can't I use the addition rule immediately right now? Well, I'm trying to find the intersect. See, probability rule, which I gave to you before, A union B is equal to probability of A plus probability of B minus probability of A intersection B. The problem, as you just said, we don't have the intersection. We've got A, we've got B. I don't know what this is. I do know what this is. I've got 3/4. I've got that one. But my job is not to find A intersection B. My job was to find A dash intersection B. So how am I going to do that? What's the point of using the addition rule? Why do I need to know A intersection B? Very good. And so this is where I mean Karnaugh Map plays a very big role here. If I can find out A intersection B, which we'll do, A union B was 3/4 equals to A, which was 3/5, plus B, which is 1/4, minus, which we don't know. We can find that out by adding both sides. So this is the question mark equals to 3/5 plus 1/4 minus 3/4. Have I skipped too many steps, or are we okay with that? We okay with this? So I just move, see that's minus the question mark. If I just add question mark on both sides, minus 3/4 on both sides, I'm here. Yeah? That means I can find out A intersection B. Let's work that out. 3/5 plus 1/4 minus 3/4. Takes a bit of fractions to work here. That would be what? That's 12 out of 20 plus 5 out of 20 minus 15 out of 20. 17 minus 2 out of 20, which is 1/10. Okay? Now, why did I want to know A intersection B? Simple. Actually, I should not do this. Let's do... Now that I know A intersection B is 1/10, see the reason why we have Karnaugh maps, we know the chances because we're talking about probability. It all has to equal 1. I can write A up here. I can write B up, A dash, B, B dash. I know the chances of getting A, which they already told me, 3/5. They told me the total chance of getting B was 1/4. And what I just found out was A intersection B is 1/10. That was the Karnaugh map that I just showed you guys. Now this is easy because now you can fill out the table. So what are we trying to find? We are trying to find A dash, which is this one, intersection B. That's what I'm looking for. So the only way to do this, now you've got the whole map. It's easy to figure out because this plus this has to give you 1/4. So 1/10 plus something equals to 1/4. You can solve it now. You can say probability of A dash intersection B has to equal to 1/10. Sorry, I should write it again. 1/10 plus something, which I'll call X, equals to 1/4. That's what we're really doing there, because this is what we want to know. That's what we're trying to find there. To find this, that's your x. X will equal to a quarter minus 1/10, which works out to be, say, out of 20. That's 2 out of 20, and this is 5 out of 20, 3/20. You can see I'm only using very basic skills here. I'm using addition rule, and then I'm using Karnaugh maps. That's all from 13A to answer question 8 of 2011 exam 1. Okay, but you can see why students find it difficult already. There's a few things that I mentioned. Complements, students don't like. Fractions, students hate. Karnaugh maps, students don't like that either. Tree diagrams you guys like. Venn diagrams, yes, no. Karnaugh maps, see that's what I'm saying. Examiners will put questions that you don't like. So anything you don't like, that's what you gotta work on. All your weaknesses are the things you gotta work on. Okay? Once you know that, it says A and B are mutually exclusive. So you still want to find the same thing, but if A and B are mutually exclusive, the only thing that changes is that's 0. You do the same thing again. If that's 0, then that has to be a quarter. Quarter plus that. That's why this is 1 mark. That's 2 marks. Simple and easy. Yeah? There you go. That's 13A. As a quick wrap up of your Year 10, Year 11 mathematics, you got addition rule, and you've got your Karnaugh maps. But we'll go to conditional probability afterwards. Likely to be tomorrow. Okay? Cool, I'll end the video there, but it's worthwhile having a look and revise your probability.